thank you for joining us today. We're going to delve a little deeper into a November article from The Leading Edge, a special topic on reservoir characterization. It's called A New Approach to Quantitative Azimuthal Inversion for Stress and Fracture Detection, Working with Effective Elastic Parameters in Anisotropic Media. Today's presenter, Peter Mesdag, he's our physics guru, holding a PhD from Delft University of Technology in the Netherlands. He's been with Jason from the start, from 1986, and has more than 32 years of experience. Peter is very strategic in the development and application of advanced quantitative data analysis techniques, including inversion, geostatistics, wavelet estimation, modeling, and reservoir characterization. He's been involved in a wide range of projects throughout the world, giving extensive international technical and business experience in the field of reservoir characterization, where he utilizes the full range of technologies available on the Jason workbench. Peter also continues to provide consulting to our clients and contribute his technical expertise to furthering research and development in geosoftware's deterministic applications. So just a highlight of geosoftware's full portfolio. It delivers solutions for the entire journey from exploration and development to life of field production management. We offer the industry's preferred set of tools and support for multidisciplinary teamwork, integrating workflows to give you the full end-to-end solution. Everything from seismic processing all the way to reservoir engineering. Today's webinar focus, we're going to be focusing on Jason. We know that today's increasingly complex E&P challenges require more robust applications and comprehensive workflows. So Jason's advanced seismic reservoir characterization workflows help you answer questions to mitigate risk. Jason has always believed in supporting critical decisions for geoscientists and engineers so they can optimize their well productivity, field development, and reservoir management. For those of you that may not know, this is the Jason full product suite overview, but for today's webinar, we're going to focus on anisotropic inversion. And Peter's going to show you that it can help you tie wells better. You can have more layer-based models. We'll go into that in just a minute.
Thank you very much, Jasmine. Welcome, everybody. Whether it's good morning or good evening, depends on where you are, but I think people from all over the world are joining here. First, I'd like to just do a little one slide on why we do azimuthal inversion. Well, in practice, azimuthal inversion is used for reservoir characterization in fractured and differentially stressed rocks. And the technical benefits of doing azimuthal inversion are that you have a layer-based model, so you can tie it to the wells. It's not interface-based. Fractures and faults can be identified. You can look at the anisotropy magnitude to hit the sweet spots in your reservoir. You can better orient your wells based on the orientation of the anisotropy, and in that way, with fracking, create optimum fracture patterns. You can measure or estimate the fracture density. You can do stress analysis. And last but not least, you can look at the seal integrity of your reservoir in case you want to be fracking. The value of doing reservoir characterization in a layer-based way is that you can have more efficient well programs, you can get more efficient and increased production, better fracture stage design, so you can avoid a water breakthrough, and of course, as you're using seismic data, it is cost effective. So this is just an intro to why we are doing this, and now for the content of today's presentation. I'm going to talk about using effective elastic parameters to identify your reservoir, and I'll explain what those effective elastic parameters are. And then to show that they actually work, I'll compare synthetics using effective elastic parameters with full anisotropic synthetics. And then as a product of using effective elastic parameters is that we can do post-inversion analysis, because we know what the inversion products should be telling us in anisotropic environment. And we can also, if we hypothesize a model, we can predict the anisotropic inversion outcome even before we do any seismic acquisition. In that way we can do feasibility studies and find out what kind of acquisition you need, or whether seismic is going to give you the answers you expect. So to get started, I'll first talk about effective elastic parameters. Effective elastic parameters are transforms of your isotropic elastic parameters, Vp, Vs, and density, and they're designed to mimic the reflectivity profile of your seismic data under certain conditions. They are not physically measurable properties, so there's no measurement you can do in your well to measure the effective Vp, Vs, and density. As an example, I like to quote Pat Connolly, who in 1999 introduced elastic impedance, because at the time there was only post-stack inversion available on the market, and Pat saw that on the far angle stacks there was more information about the reservoir, particularly about fluid content of the reservoir. So he wanted to invert the far angle stacks, and of course could not use acoustic impedance as a background model, and therefore coined the term elastic impedance, and he could use that to do his seismic reservoir characterization. Of course, since then we've taken a step forward in the market, and pre-stack inversion has become more or less commonplace. And what we're going to do now is take the next step, and with pre-stack inversion in anisotropic media, I'll introduce the anisotropic elastic parameters that allow us to use isotropic modeling and isotropic inversion in an anisotropic medium. And it's mentioned TI here because the technology I'm going to present is already in our software for VTI and HTI, but it can be easily extended to TTI and even to possibly to orthorhombic. So the anisotropic effective elastic parameters, today's subject. You can show that you can transform your isotropic elastic parameters, the capital E in here, to the anisotropic equivalent, the E prime, by a combination of the Thomsen parameters and the formulation using those Thomsen parameters. What we do here is to transform the Thomsen parameters into Thomsen reflectivity parameters, so epsilon is transformed into epsilon r by subtracting an average background. And when you do this, you can, for instance, for HTI media, rewrite your elastic parameters Vp, rho, and Vs into their effective elastic parameters Vp prime, rho prime, and Vs prime. And the formulations are given here. They look rather complex, but they are just mathematical combinations of the Thomsen parameters, the angle of your anisotropy and the angle of the seismic, and a G, which is the Vs over Vp squared. So these are effective elastic parameters, and we'll be using those in isotropic modeling and isotropic inversion. So to show that they actually work, I'll compare some synthetics. I'm going to use two routes. I'm going to calculate in route 1 my effective elastic parameters, and then I'm going to use isotropic AVO-AVA modeling. And in route 2, I'm going to use full anisotropic AVA modeling, and this method I'm going to show you here is based on Vajcek and Prinsek's method, which was published in 1998. I'm using a pretty simple model, so there are 4 layers in the model. The top and the base are isotropic. The second layer is VTI, so horizontally stratified, and the third layer is TTI. And with TTI media, I can vary the tilt angle all the way from 0, which is HTI, to 90 degrees, which is VTI. So I'll rotate this TTI medium along its tilt axis. The elastic parameters are given in this slide, and you'll see that for the isotropic layer and the VTI layer, the isotropic elastic parameters are exactly the same. That means at the zero angle there will be no reflection coefficient, and any reflection on the interface between the isotropic layer and the VTI layer is due to the anisotropy itself. The TTI layer, for TTI we use a reference, the HTI reference, so the velocities are, the isotropic velocities are the fast velocities, and these are calculated from the slow velocities in the isotropic layer by the formulations you see below. So I'm going to vary the tilt angle. The anisotropy azimuth of the TTI medium is 0, so it's north, and I'll have seismic angles varying between 8 and 48 degrees with steps of 5. So this is the first example where we have a HTI medium. So the TTI medium has a dip adjacent of 0 degrees, but if it's relative to the VTI, like in Thomsen-Russell, it's the dip of 90 degrees. But those both represent the HTI medium as the third layer. So you see there's it's a Coca plot, and you go from low incident angle to high incident angle from left to right, and you're cycling through the azimuths. So there are 4 azimuths every time. They're cycling through the azimuths for every angle. You see that the VTI layer has no reflection at 0 angle. But what is clear here is that on the left-hand side we're using full anisotropic modeling, and on the right-hand side we are using the effective elastic parameters and isotropic modeling. See that there's no difference in the synthetics, they are exactly the same. When we rotate the dip of the TTI medium to 90 degrees off the HTI, so the adjacent dip is 30 degrees and the Thomsen-Russell dip is 60 degrees, you see that it changes, but there's still there. The two synthetics are exactly the same. Rotating a bit further, so now it's getting more towards the VTI, the TTI medium is becoming more towards the VTI medium. You see that again the synthetics are exactly the same, and when we rotate completely, so the TTI medium is horizontally stratified, you see that there's no reflection in between the VTI and the HTI medium, and there is no reflection at 0 angle. That's how the model was designed. So this shows with this example that the method of calculating synthetics through isotropic modeling and effective elastic parameters is equivalent to calculating synthetics through full anisotropic modeling for this type of medium. When you make anisotropic synthetics, though, there are a few things. You already saw that the dip angles were not the same on the left and the right hand part of the panel. So you need to take care that you have the same definitions if you want to compare synthetics from different packages. So the definition for VTI is that the background medium has the slow velocities. For HTI, the background medium is typically the fast velocities, but not always. I mean, Ruger himself, when he wrote out the equation for HTI medium, he was using the fast P velocity, but he was using the slow S velocity as the background medium. So watch out there. For TTI, it's ambiguous what you choose. It can be referenced to the VTI background or to the HTI background. There are different definitions for angles. Some softwares will define the angle of the anisotropy as being the isotropy plane, and others will define the anisotropy azimuth as the angle, and those are 90 degree shifted. The TTI dip is referenced to whether you're using the VTI reference or the HTI reference. So again, it could be a 90 degree difference. And also one must realize that if you use the Thomsen reflectivity or the Thomsen parameters and the Ruger equations, that all reflectivity is first order in the anisotropy parameters. So if you translate your HTI velocities to VTI velocities, those equations are linear. Just a few things to consider when making synthetics. Then the next advantage of using effective elastic parameters is that you can do post-inversion analysis, because you know what the elastic parameters coming out of the inversion are going to be. You know how to analyze those. And if you take the logarithm of the effective elastic parameters, so the logarithm of our E prime, we find that you can write it as a Fourier series. So there are three terms in this Fourier series. There's the DC component, and there is a second Fourier term and a fourth Fourier term. So R2 and R4. So because we know our effective elastic parameters for any outcome of the inversion, VPVS or shear impedance or density, we can write out the R0, R2 and R4. We know the amplitudes of those Fourier coefficients. And for VPVS, I've done it here on this slide. I'm writing this out here. They're all quite complicated formulas of the Thomsen parameters and of the VPVS value of the background. But I'm writing it out here to show you that if you look at the R4 term, you see there's a 4G in here, and G is Vs over Vp squared. So if you take a typical assumption of the background medium, which is often used in the mathematical approximations, is that you say your VPVS is 2. That means your Vs over Vp squared is a quarter, and you see that the R4 term becomes 0. So for VPVS of 2, R4 is 0. And also for elliptical anisotropy, where your delta and your epsilon are equal, you see that these two terms cancel out as well. So the second Fourier term, or the R4, is 0, or is close to 0 if your VPVS is close to 2, or if you have elliptical anisotropy. And this is important information if you're analyzing your background medium. You can concentrate for your VPVS usually just on the first Fourier term. So the anisotropic workflow is that we first make supergathers. So for every azimuth we have a gather with an equal number of partial stacks. And then for every azimuth we do our usual prestack inversion, and the adjacent prestack inversion is called rock trace. Then we have our effective elastic parameters coming out of the inversion, the VPVS prime, IS prime, or rho prime. And these can be analyzed with this Fourier technique to calculate the Fourier coefficients and the azimuth of the anisotropy. So we can estimate the anisotropic parameters by Fourier analysis. So as a post-inversion output from this elastic volume evaluation, we can output the isotropic elastic parameters, because we know what the isotropy plane is. We know what those isotropic parameters are. We output the Fourier coefficients and the anisotropy azimuth. You can output, if you assume the Hudson model, you can output fracture density, and if you assume linear slip theory, you can output normal and tangential weakness. You could even output the Thomsen parameters, but as I already mentioned before, in the Fourier analysis only the R2 term is relevant in the VPVS, and you can't reconstruct 3 Thomsen parameters from one equation. So for that you would also have to calculate the density anisotropy, with all the issues with calculating an independent density. That is not something which will often happen. But in principle, you could back calculate the Thomsen parameters if you had all the anisotropy information. Then, as a final point, is that we can predict the anisotropic inversion outcome. If we know what our isotropic parameters are and the Thomsen parameters, we can already say what we expect will come out of the inversion, of any inversion process. Again, looking at our the same logarithm of the effective elastic parameter, this Fourier series, we've already shown that we can exactly calculate these Fourier coefficients if we know the isotropic parameters and the Thomsen parameters. This is very important if you want to do a feasibility study. In a feasibility study, in this case for HTI, we're going to take a couple of steps. First, we're going to make a model of our isotropic parameters, the Thomsen parameters, and the angle of the azimuth. And directly from that already, we can calculate what the expected anisotropy and azimuth are which should come out of the inversion. Then we can calculate our effective elastic parameters. So for every azimuth, we have our effective parameters. And with this Fourier analysis, we can calculate the anisotropy and azimuth. Then we can do forward modeling, make synthetics, either by taking isotropic modeling on our effective parameters, or we can do full anisotropic forward modeling, and we've shown that those two are equal. Then we can do prestack inversion for every azimuth and calculate the anisotropy and azimuth again. And if all was perfect, then the three boxes on the right-hand side should be giving us exactly the same answer. But there are surprises coming. So we design a model, the elastic parameters here, the P velocity, S velocity density, VPVS. These were calculated from real well logs, but just by doing modeling. So it's stochastic modeling. So there's no relationship with the actual seismic data, but it's just a synthetic case. But it looks realistic. Then the next, we hypothesize our Thomsen parameters, and here we have epsilon, delta, and gamma, and the azimuth. These were just hypothesized by myself, and note that the layering of our Thomsen, of our anisotropy, is not following any layering in the elastic parameters, because here you see that there is no contrast in the elastic parameters where I'm hypothesizing my anisotropic layers. So now we have our isotropic parameters, we have our Thomsen parameters and the azimuth. We can calculate what we expect to come out of inversion. And this is the R2 term of the Fourier analysis, both for VPVS at the top and for density at the bottom. I'm calling this VPVS anisotropy and density anisotropy. And the reason why I'm putting this up is because there's an interesting feature here. The VPVS anisotropy is all blue, so the numbers are negative. That means that the VPVS in the isotropic plane is going to be higher than the VPVS in the anisotropic plane. In the density, it's reversed. The density numbers are all positive, they're all red. That means that the density anisotropy is highest in is lowest in the isotropic plane and highest in the anisotropic direction. This is important knowledge, and it may vary depending on the Thomsen parameters. The VPVS anisotropy can flip depending on how you choose your Thomsen parameters. But it's important knowledge because the seismic data has a fundamental ambiguity of 90 degrees. You don't know from seismic measurement alone whether your anisotropy is positive with a certain azimuth or it's negative with an azimuth flipped by 90 degrees. So the choice of your anisotropy is an important bit of information when you analyze the anisotropy direction. So with this data, we can now calculate our effective elastic parameters. Here you see 6 panels, and they are for 6 different azimuths. The cartwheel at the top shows you the direction, and you see where we've hypothesized the anisotropic layer that from panel to panel the VPVS is changing. These values we can analyze with our Fourier technique, so it's the elastic volume evaluator, where for every azimuth, for every point we'll be looking at the azimuth or azimuthal information and taking out the Fourier coefficients. So the anisotropy we expected from the input data is at the top, and the anisotropy calculated from the Fourier coefficients is at the bottom. And you see these are equal, and also the azimuth is correctly estimated. So that was the second step. We can now go and calculate the synthetics, because we know our model. This is just a COCA plot for a limited number of CDPs within the model. And again, we are going from left to right, from low angle to high angle, and we're cycling through the azimuths. An extraction of the amplitudes of the purple horizon is given in the bottom part of this panel to show you that the azimuthal variation in the amplitude is small, 0 at small angle, and it increases with the angle of incidence. With the synthetic data we can do inversion. Again, we do our sectored inversion. Every azimuth sector is inverted separately, and we get a VPVS out of that. Here there's one panel where I put all the VPVS azimuths after each other. That's why you see this vertical striping where we have the anisotropy layer. And this can be analyzed again with our Fourier technique. And the top here is what we expected to come out. The bottom is what actually comes out of the inversion. Now we have to take a step back, because these two don't really look alike, and it takes a little thought. But in our inversions, our sectored inversions, we're using a simple isotropic background trend. So in the azimuthal sense, our low frequencies are not changing. And even though we're doing a full 3D inversion, so it's a full bandwidth inversion, when you analyze the inversions in a sectored way, there's no low frequency change. So the anisotropy information is fundamentally band limited. And what you're seeing here is a band limited signal, which has been where we've chosen the branch. We said everything is blue, so you only see the positive numbers, and where you have side lobes, they're also interpreted as positive numbers. And those, where you interpret the side lobes, you see that the angles on the right and the lower panel, they are flipped. So where we are in the main lobe, we have a correct azimuth, and where we get the side lobes, our angles are flipped by 90 degrees. Now this is the case we can show because this is a synthetic experiment, and what I used here is a shallow type of survey wavelet, and it has a pretty high cutoff frequency. On the upper right hand panel I'm showing the wavelet amplitude spectrum, and you see there's a cutoff frequency of about 20 Hertz. If I apply that cutoff frequency to the top panel of our previous slide, you get the panel you see here, where you see the main lobes of our seismic of our signal are blue, the side lobes are red. And in the lower panel you see it's kind of a similar situation, only we are choosing a branch. We're saying everything should be negative. So where we have chosen incorrectly, where the top panel is red, you get the azimuth, which is flipped by 90 degrees. And this is again a synthetic example, so I can put in a different wavelet to show the concept again. I put in a wavelet with a cutoff of 6 Hertz and redo the experiment, and now you see it's much more pleasing result, where again we're capturing the anisotropy more or less correctly, but where we've incorrectly got our branch, we still don't have our 0 to 6 Hertz frequencies, so we still have side lobes in the data. So there are reds on the top panel, and those show a flip of 90 degrees in the azimuth in the lower right hand panel. So that was a synthetic example. Now just an example from a paper which we published at the SEG in 2016. What we see here is the Marcellus shale example. This is courtesy of multi-client from CGG, who allowed us to use these data. There are 4 panels here. The top left-hand panel is the first Fourier coefficient of the anisotropy of the VPVS, the B1 of the VPVS. The panel below that is the azimuth, and the right-hand panels are the isotropic parameters coming out of the volume analysis. There's a VPVS at the top and P impedance at the bottom. And if you follow the anisotropic layer, it's actually the layer which has a high VPVS and a high P impedance. But when we zoom in to the top of the structure, which I'm doing on the next panel, you'll see that there is a discrepancy there. And so the top panel, again, I'm showing a zoom of the anisotropy, so that's the first Fourier coefficient. The bottom panel is again the azimuth. But there are 2 horizons on here. There's the yellow, there's a white horizon. That one was tracked on the seismic data and follows the P impedance layer, while the black horizon is tracked on the anisotropy. And you see that in the crest of the structure, that the anisotropy does not follow exactly the layer which you would have interpreted on the seismic data. In fact, where your layers are flexed considerably, the fractures actually extend into the layers above, and the anisotropy actually does not exactly coincide with your layer anymore. And that's important to know, because if you analyze the azimuth of the anisotropy, if you follow the black layer or the white layer, or the black horizon or the white horizon, you get into the ambiguous situation where you're going from 90 degrees to about 0 degrees. So you have a 90-degree flip. So when we extract the information along these layers and put it in a map, with the previous section where you're going from north to south, from A to B, you see that in the north, which was on the left-hand side of the previous section, we are in the high anisotropy, and in the below halfway we're getting into a lower anisotropy. And if we track the anisotropy horizon, you get the top 2 panels. So the azimuth is consistent, it's more or less east-west. But if you look at the bottom panel, where you're tracking the seismic horizon, you see that the lower part of this map is coloring purple to blue, which is more in the north-south direction, so you flipped your azimuth. And if you drill on this map, you would be drilling in the wrong direction to frack your wells. So that's a word of warning based on this case study. So in conclusion, we have talked about effective elastic parameters, and they allow us to use our isotropic prestack modeling and inversion. So they exactly predict the outcome of complex anisotropic synthetic modeling using isotropic algorithms. They allow us to fit sector inversion using Fourier's techniques, and they allow us to predict the outcome of isotropic inversion in an anisotropic medium, because so we allows us to do feasibility studies. And we can do post-inversion analysis, which can be linked to fraction and stress models as you wish. So that more or less ends my presentation. So we have some time now for questions if you have any.
All right, there's one question. So in your synthetic comparison section, you use the TTI layer. How do you incorporate TTI model in your effective elastic parameters and post? Yeah,
that's a good question. These effective elastic parameters, I've been showing you in the slides the HTI representation. So I showed you the formulas for HTI medium, but we also have them for VTI. And for forward modeling for the TTI medium, we have them for TTI. So you can define your dip and everything within a TTI medium, and it'll give you the effective elastic parameters for that TTI medium.
Great, okay. And one more question. How does the effective elastic parameters approach relate to ProAZ?
That's another good question. That's a question which I personally I've always been working with seismic inversion, so layer-based properties. But there are equivalent techniques which you can do on interface-based properties, and typically if you do AVO analysis, you're looking at interfaces and the interface between two layers. So people will do AVO analysis on their seismic data, and then you can also do reservoir characterization with that kind of techniques. But we typically do inversion, and then we go to layer-based properties. So if you're talking about ProAZ, what they do in ProAZ, what we do in ProAZ is that we calculate the intercept and the gradient for every azimuth, and then we analyze the gradient as a function of azimuth. So it's the anisotropic gradient, and here that's typically where you're analyzing the reflectivity between two layers, where with inversion you go to layer properties with the advantage that you can overlay a seismic and that you can QC things better and that kind of thing. So it's a good question. It's the difference between looking at interface properties versus the layer properties.
Perfect. Thank you, Peter. As mentioned in the beginning, we have some reference material that Peter mentioned in this presentation here for you, and we'll be sure to send out these links to you. Also, if you'd like more information on Jason's azimuthal inversion, you can go to cg.com/anisotropic. And also available on the website, we have a variety of online resources available to you. We have other webinar series that are featured on demand that you can watch at your own leisure. We have a tip and trick section to help you visualize some of the key concepts in our software, training and events coming up for next year. We have a glimpse into next year. And we also have a free software evaluation if you'd like to test drive any one of the tools mentioned today or any other products listed on our webpage. So if you'd like to ask Peter some additional questions that you probably did not get a chance to ask today, you can send him an email, peter.mensdag@cg.com. If you'd like more information on other products or have additional questions, you can send an email to gs.solutions@cg.com. Again, we thank you for joining today's webinar.